welcome to the fourth annual PIRE PI meeting and workshop. And good evening to our friends who are joining us from Europe and Asia. So for today's lecture, I'm going to give you a brief overview of the project and research outcomes and broader impacts from Kansas State University for the past 1 year. Okay. So this is how I have arranged the lecture. So about 50% of the time is dedicated to broader impact. Okay. So the PIRE project, right? The PIRE stands for Partnerships for International Research and Education. This is a very large international research and education initiative on researching certain low-cost silicon-based pre-ceramic polymers for making high-temperature non-oxide ceramic fibers for CMC applications. Okay, and so we have split research into 3 themes and the education component also into 3 themes. And so the research thrust 1 is focused on the polymer state. So here we are researching different classes of pre-ceramic polymers with different functional groups and assessing their spinnability for fiber drawing. And second one is the research involves the ceramic state. So here we are characterizing the ceramicized fiber, microstructure of the ceramic fiber, polymer to ceramic yield. And then we have research thrust area 3, which involves development of tools for high temperature oxidation and mechanical testing of these pyrolyzed ceramic fibers. And also correlating that with the microstructure of the fiber as well as the molecular structure of the starting pre-ceramic polymer. So these, and then as far as education is concerned, we have 3 themes or 3 thrust areas. The first one involves the short-term research for undergraduate students with the goal to have young researchers get excited and involved early into the field of polymer-derived ceramics. Then we have education theme 2, which involves this organization of the PIRE workshop as well as symposia at national, international conferences, and also short course offerings with the goal to promote research outcomes from the project, as well as to expand the scope of PDC materials. And then the third one, ET3, education theme 3, involves joint supervision of graduate students, as well as starting dual degree programs with our partners across the Atlantic. So these research thrust areas as well as education thrust areas, based on these research thrust areas, we have selected partners with expertise in one or more of these areas. Okay, and those partners are listed here. With this, I would also like to give a shout out to our non-US project partners. Especially Professor Ralph Riedel and Gabby Mera. Professor Riedel is here joining us in person, and Professor Miele, Professor Salami and Barnard from France, and Professor Colombo and Professor Soraru from Italy, and Professor Gervais from Sorbonne University, who is our go-to person for NMR. So we really appreciate you helping us into the third, we just completed 3 years of the project, so we appreciate your continued support for this effort. I would also like to mention that there is one change. Professor Rishi Raj, who was our project participant from University of Colorado, is not going to be continuing. Nonetheless, we thank him for his help in initial team building, as well as pushing us to pursue joint funding. I also like to thank him for stepping aside when he was not able to contribute to the project in a meaningful manner. Also remembering those who have lost in the past 1 year, we have lost Professor Masaki Narisawa from Japan. He passed away early this year. Although we never really had a very strong research collaboration with partners in Japan due to IP-related issues. Nonetheless, Professor Narisawa was a very strong proponent of the PDC workshop, as well as our education efforts. Professor Narisawa attended all 3 of the workshops, and we're going to miss him. So moving on to the research projects and outcomes from Kansas State University. So I have 1 slide each on different projects that we worked on the past 1 year. Oh, to begin with, these are some of the journal papers that were authored by NSF PIRE PhD student as first, as lead author, and the student has since graduated. So on an average, we try to get 10 to 15 journal papers and 40 research product as a PIRE team. Okay. So this was the key outcome from fiscal year 1. So as you know, we are interested in development of low-cost silicon-based pre-ceramic polymers that are readily processable and easily available within the US. So our initial efforts were focused on oligosilazanes and oligosiloxanes. Majority of these are liquid phase at room temperature and do not possess the right rheology for fiber drawing. So nonetheless, these pre-ceramic polymers, one may induce low temperature thermally induced cross-linking and try to tune the rheology, as can be seen here. However, many of these low temperature thermally induced cross-linking reactions are not controllable. So as a result, what happens is if you heat the pre-ceramic polymer, there is sudden change in viscosity and there's insufficient time to draw fibers from. And once the material solidifies, it's infusible solid and it's not meltable anymore. So you cannot apply, generally you're not able to apply melt spinning processes. So in order to find a solution, my first NSF PIRE PhD student Zonkan, based on his review of the literature, was able to introduce certain spinning agents to tune the rheology of the oligomers. And so he tried different organic polymers, linear, high molecular weight, at different weight loadings into this commercially available silazane. And he came up with this process of hand drawing. And we demonstrated that long uniform fibers could be produced by introduction of PAA into oligosilazane. This is an 8-member ring, and these are some of the fibers that were produced as part of Zonkan's thesis. Later on, toward the final leg of his PhD thesis, Zonkan was able to actually take it to the next level, and he was able to produce large area non-woven ceramic fiber mats from, in this case, oligosiloxanes. In fact, he studied 3 different types of siloxanes, and this is 4TTS, T3TS, and this is platinum complex TTCS. And he was able to demonstrate these fiber mats. And more recently, I have a new graduate student, Shakir, sitting over there. And he has conducted some high temperature oxidation tests on these fiber mats. And what we observe here is that the platinum containing TTCS leads to the highest silicon content in the pyrolyzed ceramic. That's number 1. It also has it seems to offer the highest oxidation resistance in the 800 to 1000 degrees C temperature range. And these are some of the SEM images before and after. So Shakir is presently involved in measuring the oxide scale thickness, and you will hear from him in his presentation tomorrow. Then Shakir's core thesis project involves oligosiloxanes that are linear, and this is based on literature review. It seems like pre-ceramic polymers with linear high molecular weight appear to be more amenable toward drawing processes. So we selected these 3 oligosiloxanes, and indeed Shakir was able to hand spin as well as spin these pre-ceramic polymers into fiber mats, and these are the images after pyrolysis. And this is the TM image of these fibers, different types. And so the key observation here is that the fiber microstructure and the diameter of the pyrolyzed ceramic fiber correlates with the molecular weight or molecular mass of the pre-ceramic polymer. So higher the molecular mass, larger is the fiber diameter. That's one thing. Also, the diameter of the fiber produced via shorter oligosiloxane are generally hollow. So this is something we are looking into, and this research we are also getting support from Professor Crystal Gervais, who is conducting NMR for us. So that's that, and then this is one other project that Shakir contributed to. This is a project that involves Quartz optical fiber based sensor material, and the objective here is to improve the high temperature capability of the Quartz based optical fiber. And this is a project that is related to PIRE but not funded by PIRE funding. And so Shakir was able to demonstrate uniform coating of silicon boron carbonitride on meter long optical fibers. And from our initial testing, this SiBCN coating improves the high temperature capability of the base quartz optical fiber. Then this is another research project. This is a master's thesis project of another graduate student, Sanjoy Day. He will be joining us. He's not here physically, but he will join us. He will be joining us via Zoom. So this project involves introduction of nanosheet material into polymer-derived ceramic fibers with the goal to improve mechanical properties as well as high temperature capability of this ceramic fiber. The primary motivation for this works comes from this paper in Science magazine last year, in which exfoliated graphene was introduced into PAN, and then upon carbonization, these graphene containing carbon fibers offered 2 to 4-fold increased modulus as well as breaking strength. And this was achieved at actually very low weight loadings, about 0.07% weight percent graphene in carbon fibers. So what Sanjoy is doing is he's looking at other analogous 2D materials, for example, boron nitride and TMDs. These 2D materials also offer superior mechanical properties compared to everyday engineering materials, but they have one advantage over graphene, that they have higher oxidation resistance compared to graphene. Graphene generally burns at 400 degrees C. So you will hear from Sanjay in tomorrow's session. Then as far as undergraduate student summer research projects are concerned, this year we mentored 3 undergraduate students at K-State. So Mabel Anstine is going to be a junior in fall in mechanical engineering at Kansas State University, and her project involved documenting mass yields of 3 oligosiloxanes. Actually, these are same oligosiloxanes that Shakir had used for fiber spinning processes. The difference here is that Mabel was assigned these pre-ceramic polymers without any modification. So there's no spinning agent involved. And so her project involved documenting the mass yield from polymer to from oligomer to cross-linked polymer, from cross-linked polymer to pyrolyzed ceramic, as well as utilizing a range of spectroscopy techniques to understand the cross-linking mechanisms. So the 3 key observations from her research are: number 1, all 3 of these linear siloxanes had extremely low ceramic mass yield. That's one. And then the mass yield of the ceramic correlates with the molecular weight of the pre-ceramic polymer. So higher is the molecular. So for example, EDTS has the highest ceramic yield compared to, for example, DTDS. And then another observation was that, which is very interesting, that majority of the mass loss occurs after cross-linking. So during the pyrolysis stages is when the majority of the mass loss is occurring. So we are able to cross-link these pre-ceramic polymers, and they solidify into white epoxy. But then the ceramic yield is negligible. Actually, in this case, it's less than 5-8%. Also, Mabel has utilized FTIR to get the bond conversion yields. So she would do the FTIR of the pre-ceramic polymer after cross-linking, and also pyrolyzed ceramic that's produced from the pre-ceramic polymer, and look at the intensity and there are some equations involved, and you can get the bond conversion. So she's able to explain the mass loss based on the chemistry. Then another project, Dylan Kruep. Dylan actually just graduated. He just finished his undergraduate degree from K-State. He worked on 2 or 3 different projects, but his key project involves mechanical property assessment of certain commercially sourced silicon carbide fibers. So he was assigned 3 silicon carbide fibers that are shown here. And so Dylan would use these ceramic fibers and prepare polymer matrix composite of 2 types, discontinuous randomly distributed fibers as well as continuous long aligned fiber matrix composite. And you then conduct the tensile test. And so here's some of the results here. We clearly see that obviously one result is obvious, which is fiber containing composite is significantly stronger and stiffer than neat epoxy. But the other result is that the high nickel-on fiber containing composite showed significantly higher breaking strength. Okay, and also Dylan was able to utilize micromechanics of composites to get the theoretical predicted values for longitudinal and transverse modulus as well as the breaking strength, and compare that with experimental observations. Dylan also contributed to another project that involved oxidation of conducting oxidation tests on ox-ox composite as well as high temperature ceramic adhesives. And for this, he got some advice from Dr. Sarah of Spirit Aerosystems, who is also here with us. Dylan has taken up a full-time position with Spirit Aerosystems starting next month. And Dylan was also the outstanding graduating senior from our department this year. The third student, Ellie Christman, she is undergraduate student in chemical engineering at Lehigh University. Her main advisor is Professor Himanshu Jain. So Ellie was with us for about 4 weeks at Kansas State University, and her research involved just learning fiber drawing processes and characterizing them via electron microscopy and spectroscopy techniques. So she was assigned this oligosilazane. This is, as you can see, this is 6-member, and the previous one that we worked with was 8-member. So the idea here is to see if, we wanted to see if the size of the ring has any effect on the spinnability of the pre-ceramic polymer. And so she would draw fibers from these pre-ceramic polymers. And so the key observations were that the 6-member ring silazane is more amenable to fiber drawing compared to 8-member ring, and then also at lower weight loadings of the spinning agent. So that's one observation. And I think another one was that she looked at the mechanisms during cross-linking and pyrolysis, and she found out that it's the dehydrogenation as well as vinyl polymerization that are play at low temperatures, and then eventually it's ring opening mechanisms and formation of SiO network in which oxygen is replacing nitrogen, especially if the processing is done in open air. And so you will hear from her in her tomorrow's lecture. And I would like to mention that Ellie is also co-advised by Crystal Gervais. So the next step for us is to conduct NMR analysis and see how that compares with her observations from FTIR. Ellie is also now a certified independent operator of XPS, Raman, and FTIR. She has received those trainings at University of Nebraska-Lincoln and University of Kansas. This is like 2-day long training for equipment. So then with this, these are some of the other research outcomes from Kansas State University. These are some invention disclosures and patent applications co-filed by PIRE students. And the red ones here are from this funding cycle, green from previous funding cycle. And the idea here is that someday we'll be able to take what's happening in the lab to the marketplace. And then these are other outcomes, conference presentations, again with graduate student as first author, and prestigious ones, like for example, ACS here, and then IMechE for mechanical engineering, and then ICACC for American Ceramic Society. I'll move on to broader impacts. You know what broader impact is. If you don't know, then this is the definition I found at Harvard University. The potential for a research project to benefit society or advance desired societal outcomes. Okay, so with this, so student impact on students. These are our PIRE scholars, graduate students, to graduate in the past 3 years. So these are the students who contributed significantly to the PIRE project, and these three here are partially contributed to the PIRE project. And these two students were mentored by Professor Kroll, and the Casey was mentored by Professor Navrosky, and Zonkan by myself, and then Susanna also mentored by Professor Kroll. And Davi has also graduated. He is moving to Detroit. He's accepted a position with Exalt Energy. And then we also had one student from Italy who was co-advised by myself, and but his main advisor, Professor Paulo Colombo. Federico worked on CMCs, directing right of CMCs for energy storage applications. And we hope to get more students from that group in the future. So these are our current students. Shakir and Sanjay, I already discussed their research topic with you. Shakir is here. Sanjay will join us via Zoom. And then these are the graduate students from University of Colorado, Ali Badran and Spencer. Ali's research involves quantifying development of damage in CMCs under varying loading conditions, and also quantifying the evolution of microstructure in CMCs by use of X-ray CT and automated image analysis, deep learning algorithms for automated image analysis. And I think you're scheduled to graduate sometime this year. And then Spencer was our, Spencer actually started with us as an undergraduate PIRE scholar, and then he decided to pursue his PhD with Professor Marshall. Spencer's research primarily involves additive manufacturing of CMCs. He's also a co-founder. He has he's the founder of a startup company called Mac Electric. Both of these students have shown strong leadership and organization skills. I think they have a very bright future. And then these are graduate students from other partner universities. We have a new student at Lehigh University, Joel Garcia. Joel actually just graduated. He hasn't even started his PhD yet. He'll start his PhD in the fall term. So Joel graduated from University of St. Thomas, and he spent a summer with us before joining Lehigh. So he was involved in that graphene reinforced PDC fiber research. And then Sharik and Akshada are graduate students from UT Arlington. Sharik's research involved computational modeling of PDCs. Akshada, she's involved in, her research is experimental in nature. And you will hear from these students in tomorrow's session. From Arizona State University, we have this very bright young man, Jerson Lonell. Jerson is got his bachelor's degree from Washington State University, and he's now working with Alex on high temperature calorimetry of silicon carbide fibers. Jerson, prior to Jerson, we had another graduate student, Michael Bustamante, and Michael is also here. Michael has received a prestigious NSF scholarship, so he's working on another project related to high temperature materials, but not PDCs, but still with Alex. And then I believe our students have done well. Research is getting attention. Ali Badran's paper received Best Poster Award by the University by the Journal of Material Science. And these are just few examples. I'm sure there are many more. These are the three that I was aware of. And then undergraduate student mentoring at other universities. So I already talked about Mabel and Dylan and Ellie. We have 5 additional undergraduate students. So Carla, Hannah, and Jonathan, they are here. They are being mentored. Carla and Hannah, they are mentored by Professor Kroll, and their research, I think, involves, one is, I don't know which one is doing computational modeling, but one is doing computational modeling, the other is doing experimental research. So we'll know that tomorrow, right? So, and then Jonathan is mentored by Professor Marshall, and his research involves deep learning, use of deep learning algorithms for automated image analysis of CMCs. And then 2 undergraduate students from Arizona State University. Wyatt is here, and he is conducting high temperature calorimetry on phase pure silicon carbide. And Langston's research involves porous, similar kind of analysis, but with porous silica. And then integrating research and education. These are some of the lab modules that I had introduced since the beginning of the PIRE project. Last year, we had to move everything online, so we switched to ANSYS. And this is the lab module that my graduate student who was GT at the time developed. So utilizing ANSYS for fiber matrix analysis in CMC structures. And then with Alex introduced this crash course on high temperature calorimetry in the midst of the pandemic. And she had about at least more than 50 students attend this course and all throughout the globe. And some are not even affiliated with the PIRE project. And you can find information related to this course. This is just one example. She has introduced other courses related to this topic. And if you go to this website, Alexandra-Navrotsky, you will find information about Alex and courses that she has introduced throughout her career. And this is Alex from 1969. Okay, so the FIRE workshop, the goal here is to network, right? Promote the research outcome as well as connect with industry and get feedback from the industry on what we are doing. So we had the first workshop was held at Kansas State University. We had 45 attendees. Second workshop was held here in Boulder at University of Colorado campus, and we had 55 attendees. We saw increased participation by industry partners. And then we had this is third workshop we had that was in virtual mode. And here we had over 100 attendees. Increased participation by industry members, also program officers from different funding agencies, as well as international students, and also participants from national lab. So the one way we measure the success of the workshop is through Qualtric surveys. These are surveys not conducted by us, but by a third party. And so we continuously see these high numbers with regard to successfully expanded scope of PDC materials and improved face-to-face interactions. So I think this shows that I think this is a measure of success and shows that we have done well in the past. With regard to international partnerships during the pandemic, I think this was not as difficult as I had originally anticipated. We have been able to switch to Zoom-based meetings. In fact, we have our Zoom-based meetings, sometimes formal, sometimes informal, bi-monthly. And then not all of our international PIRE participants are able to contribute in the same manner. It depends on their situation back home. But I would like to mention at least these three names here: Crystal, Gabby, and Crystal Salami, who have continuously mentored students from our group and also partner universities, and Professor Colombo as well. And then I continue to serve as an external thesis examiner or co-advisor for students outside of the US. And some of the two students are listed here. And some of the visits actually got postponed. I was expected to host student from Professor Colombo's group and also from IIT Madras and Brazil. It's just the interview, they keep postponing the visa interview. So let's see how it goes. Hopefully we will have these students toward the end of the year. And by the way, these are the pictures from our last meeting. This is from late January, early February ICACC last year, just before the pandemic. And this is from my visit to IIT Madras in January 2020. And this is our collaborator from Germany, and this is our collaborator from IIT Madras. And then we have continued to organize joint symposia to promote PDC materials. Most of the time I'm a co-organizer and my name is put in. So I'm very grateful to our to Professor Riedel and Professor Colombo for making me part of some of these events. But the key one here is in 2021. It's the MSNT, and we are organizing a symposium on PDC materials. This effort is led by scientists at Air Force Research Lab, and Professor Colombo and Gunter Moos are the co-organizer along with myself. And we're on to the milestone chart. So this is the chart from at the time of the proposal submission. I think we have done well in research thrust area 1 and 2. Research thrust area 3, which involves mechanical and high temperature behavior of fibers. I think it got pushed by about 6 or 7 months. Nonetheless, I already showed you that we are onto it. But we have a no-cost extension from NSF for a year. So I believe we will be able to catch up. But we have done particularly well in these education themes. I think it was much easier to pivot to online learning. And also Celis had done very well in communicating the research findings through social media. I thank him for that. Also, then comes the question, we are into the 4th year of the PIRE project. It's a 5-year project. What's next? So we're looking at those as well. There are a couple of solicitations out with regard to high temperature materials, especially, and there is a clear mention of Cyclic. So, but these are manufacturing related solicitations. And once you start working on a hypersonic related project, that would automatically mean, less collaboration with the international partners. Nonetheless, I think these are good opportunities for those of us who are based in the US. But I think there are other opportunities out there which have strong research as well as education component. And some of you are already aware of this, maybe the MRSEC, MRS, the Material Research Science and Engineering Centers. I know University of Colorado is presently working on such a proposal, but these are very large efforts. So we're talking about 4 or 5 million per year. And there are also engineering research centers. So I think if we get these kind of grants, then we will have strong education component as well as international component. So my plan is to learn more about these proposals, maybe serve on a panel, and also meet with the program officers who handle with these kind of proposals. Also maybe visit universities who have these grants, who have received these grants in the past 1 or 2 years. So just try to educate myself. So with this, I would like to thank National Science Foundation for the financial support. And so thank you.